Hello everyone and welcome back. So we have a few minutes before the official class start time. If you would like to ask me a quick question. Good morning. Question, can I tell you when is our final exam? No. I'd like you to go and look on Carleton Central or the Carleton final exam schedule. That information is posted there. I don't like to announce these things for a couple of reasons. One is if I make a mistake, then it's my fault if you miss your final exam. The other is occasionally these lectures get reused, these recorded lectures, and I would hate for somebody to be watching an old lecture and see me announce the date of the final exam in that lecture, which wouldn't apply to them at that time. So please look at the Carleton exam schedule. We'll be following that, with the exception that I asked them to schedule a 2-hour exam, but they actually scheduled a 3-hour exam. But it will be a 2-hour exam. Okay. So today we're going to do something different in the sense that normally, so what we're going to do today that's different is we're going to talk about something that is related to current affairs. So normally I try to make my lectures as irrelevant as possible. Unfortunately today we'll see something that's actually rather relevant these days. And it's a nice application of probability, and it's a nice example of how the way we do things in computer science actually can help in a lot of ways. In the sense that in computer science we're interested in algorithms, which is about efficient use of resources, so you doing things as efficiently as possible. And it happens a lot in other disciplines as well, that you're interested in the same things, and sometimes computer science, the computer science way of thinking can shed some light on it. So the motivation comes from testing for disease. So imagine you have a population of people, so they're going to be called, let's say, P1 through Pn, so you have n people, and k of them are infected. Okay. So what are they infected with? Well, it could be whatever it is you happen to be studying. It could be coronavirus, it could be Ebola, whatever you like. And it's important to be able to identify these K people who are infected. And the way you identify them is that you, you do tests. So you take samples of, in this case it's nasal swabs from these people, and you do some, whatever you do in a lab, to detect if in that nasal swab there is basically the DNA from coronavirus. And if there is, then that means that person has an active coronavirus infection. Similar thing is done for Ebola, except you use blood samples rather than the nasal swabs. But it's the same idea. Okay. So you have N people, K of them are infected. You would like to figure out exactly who is infected. And so you think, well, I mean, if you need to find them all, then the only thing you can do is test them all, right? It seems there's no way around that. And that's kind of true. But in testing, there's a sort of a dichotomy. There's sort of two things that have to happen for testing. Is if I want to test someone to see if they're infected, well, I have to collect a sample from them. Okay. So right now, the way it works in Canada, and I've done this twice now, is for COVID, you do a nasopharyngeal swab, which actually is worse than it sounds. They get the sample from the back of your throat, but they get it by going in through your nose. Really not pleasant. But it's still relatively easy. And by that I mean you don't need an advanced degree to be the person who takes that sample. So it's a fairly easy job. Anyone with a bit of medical training can do it, and it's fast to do. But then that sample has to go off to a lab somewhere where they do the actual testing to see if the sample contains whatever it is, DNA or RNA from the virus, and that's difficult. It's expensive. It's slow. So that's the painful part. So collecting is usually easy. Testing is more difficult. In fact, for many things, collection can be done sort of at home. I mean, it's a little bit trickier for COVID, but for lots of things, you can imagine that the collecting can be done at home. The testing has to happen in a lab. And there's assignment 4 is still due on December 6th. I was wondering, because CU Learn does not have the hand-in link yet. Yes, assignment 4 is still due on December 6th. Thanks for reminding me. I have to create the assignment on CU Learn for you guys to submit something. I will do that immediately after this lecture. Okay. And here's the other thing that you can do. The way these tests work, they're looking for specific DNA or some specific thing in the sample, and they return positive or negative based on that. You can do what's called pooling. and that swab gets some of the stuff from the back of your throat and gets it doesn't look like much when you look at it with your bare eyes, but it's a pretty big sample. In fact, there's enough in one of those samples to do several tests. And if you think about the way the test works, it's looking for the genetic material that makes up the virus. So if I take two people's swabs and I put them together and mix them up in a test tube, then if either of them has the virus, you're going to find the genetic material in there, and the test will come back positive. And in fact, with current COVID testing, you can actually combine up to 16 samples from different people, and if any one of them has COVID, then that test will come back positive. Okay. So that's interesting. Does that save us anything? Can we do better? So let's think about a really simple example. What if there are N is 1 million people? And out of those 1 million people, I know that one of them is infected. So if I just do the obvious thing, then I would have to do 1 million tests, expensive tests, to find the one infected person. So could I do better than that using this idea of combining samples? And the answer is yes. So let's take 1,000 groups of 1,000 people each. That's 1 million people, right? 1,000 groups of 1,000 people, that makes 1 million people. Test each group. So that means, you still have to collect 1 million samples. So you have to collect a sample from each person, but maybe each person can collect their own sample and just mail it in. So you test each group. So that is 1,000 tests. And that really means you take this group of samples you have, there's 1,000 samples in that group. You cut them in half and mix half of them together. So 1,000 samples are in there, but you still have some, for each person in that group, you still have some of their sample left not mixed. But then you have the mixed part, which contains the samples from 1,000 people. You test each group. And if only one person out of the 1 million is infected, then exactly one of the groups will come back with a positive test. Exactly one group will test positive. Right? And now what do? So let's call it G, one group G will test positive. You individually test each sample in G. That's 1,000 tests. Okay? So in one of the groups, the infected person is there. That group will test positive. And then you test each of the samples, the individual samples in that group. And 999 of those will come back negative, and one of them, exactly the one with the person who's positive, will come back positive. And then you'll have identified the person who has this infection. And how many tests did that take? 1,000 tests, one for each group, plus another 1,000 tests, one for each person in the group that tested positive. So you get a total of 2,000 tests. So in this sort of extreme example here, you go from having to do 1,000,000 tests if you did them individually down to 2,000. Okay. So pretty big speed up. So it's a factor of 500 in the savings in the number of tests that you have to perform. And so good question. So someone says, why not divide the 1,000 again into further groups of, say, 100 or 50? That's an excellent question. And, well, there could be lots of reasons you don't do that. For instance, maybe you only have enough whatever material from each person to do 2 tests, right? So you cut the nasal swab in half. You save half for if you need it later, and the other half goes into the mixed up thing. So that's one possibility. The other, I guess, and in fact, that's a good question. The other thing is, this is a discrete combinatorics and probability course. If I was teaching a data structures course, this would be a nice problem. And in fact, if you think about it data structurally, so if you're willing to do more rounds of testing like that, so why did I take 1,000 people in each group? Well, I took 1,000 because it's the square root of 1,000,000, and I wanted to do 2 rounds of testing. And what if I was willing to do 3 rounds of testing? Well, then you could see you could make groups of this cubed root of 1,000,000 people, that many groups of them. And then one of the groups comes back positive, then you break that up into another groups of cubed root of 1,000,000 people. Inside of there, one will come back positive, and the third thing is a group of size the cubed root of 1,000,000, and you sample that. So if you're willing to do 3, you can do even better. You get 3 times the cubed root. And more generally, if you have no upper bound, if you're willing to do as many tests, sort of rounds of testing as you want, then probably the best thing to do is to break first into 2 groups of 500,000. You do 2 tests, and now you have to recursively solve the problem on the group that of size 500,000 that has the infected person in it, and you log n rounds, so log of 1,000,000, so that's about 20 rounds, and in each round you have to do 2 tests. One will be on the subgroup that contains the infected person, and the other one on the subgroup that doesn't. So if you're willing to do as much as you want, instead of 2,000 tests, you could actually get this down to 40. So that's a possibility, but it becomes more difficult to manage, and there's lots of other sort of questions which are how long these tests take. So, and I don't mean how long a person has to work to make the test happen, but how long some chemical reaction will have to take. Because if that takes a while, then maybe if you have to do 20 rounds of this to find the infected person, each round takes a day, that might take you 20 days. Whereas here, this would take you 2 days. So lots of, there's lots of sort of real world issues that come into this problem that might allow something like that, or maybe not. But here we're going to study where you want to do just a few rounds of testing. But in general, to find one person, you could do log n rounds of testing and find that person that way. All right. But this is too easy. And why is it too easy? It's too easy because there's only one person infected. Usually for diseases and things, that's not the case. There's like some fraction of the population is infected, and we'd like to know what we can do in that case. So we want to find a procedure that doesn't do too many tests, and yet is still guaranteed to find all of the K infected people. Okay, So that's the setting. We have people P1 through Pn, and we might as well assume that, well, no, we have these people P1 through Pn. Someone tells us that K of them are infected. This is probably the most sort of iffy assumption here, that we know exactly how many people are infected. But actually we'll see that even if you don't know exactly how many are infected, as long as you have a pretty good estimate of this value K, like maybe you've been, you're testing the population every few days or so, then the results, the fraction of people infected in the previous test give you a good projection of how many are going to be infected in the next time you do this. So just to make our lives simple, we'll assume we know the value of K exactly. Yeah, and we want to do, let's start with the simplest thing, which is called single pooling, which is a scenario exactly like this. We break it up into groups, all of the same size. We test each group, and then some of those groups come back positive, and we then have to test the individuals in each of those positive groups. So we break or partition into n divided by s groups, each of size s. Each of size little s. And then we, and let's call those groups G1, G2, up to Gn divided by s. We test each group Gi, and if Gi tests positive, we test the individuals. So testing each group Gi, there's nothing really to study there. We have n over s groups. That means we have to do n over s tests. And if Gi tests positive, then we have to test the individuals in Gi. And so that means we have to do s tests for each of those positive groups. And because we don't know anything, perhaps the best thing to do is to do a randomized trial, a randomized sort of testing procedure, where this partition into groups here, we want it to be random. And probably the best way to think of this is P1 through Pn should be maybe a random permutation of all of the people, all of the n people. Okay. So let's say this is a random permutation of n people. So if that's random, that's the only thing that's random. When we partition into groups, you can imagine we just say that the first group consists of P1 through PS. The next group is P s plus 1 up to P2s. Right? So we have, here's the first group, P1, P2, up to PS. Then the next group is PS plus 1, PS plus 2, up to P2s. That's the group G2, and so on, all the way up until the final group, which finishes at Pn, and and this must be P n minus S plus 1. This is group n over S. So this is a probability question, which means we would need to know the universe. And so the universe then is the set of possible permutations here, right? So some of the people are infected. So it's exactly k of them, though. There's nothing random about that. And then, but there's a random permutation of the people. So, you know, S is the set of permutations of these n people. And the probability measure is going to be uniform, so it's a random permutation, meaning each one is equally likely. So each one has probability 1 over the size of S, and the number of permutations is n factorial, so any particular permutation has probability 1 over n factorial. And what we'd like to know is, if we do this, then what's the expected number of tests that we have to do? And then maybe we can choose the value of S to make that as small as possible. So we're going to say let X be the number of tests performed. And we would like to know what is the expected value of X. We just saw an excellent example when n is 1,000,000 and k is 1, that we can make the expected value of X 500 times smaller than n. So maybe, you know, it'd be good to know this in general. All right, so how are we going to do this? Well, what do we know about X? X is equal to, well, there's some things we know for sure. These n over S tests always happen. So we have to test each group. There's no option there. So it's n over S plus something. And that something is, it's really about how many of those groups tested positive. And each time a group tests positive, that's S more tests that we have to do. So there's lots of ways we can tackle this. In particular, we could look at the probability that a particular group tests positive. But for what's coming later in the class, when we do multiple pooling, we'll see that it makes more sense to look at it a different way. And the way to look at it is, for each person, we will look at whether or not they had to be tested, their sample was tested in the second round. So whether their sample was tested individually. So for each I in 1 up to n, we're going to define an indicator variable, xi, which is going to be 1 or 0, and it's going to be 1 if PI's sample is tested individually in the second round, individually, and 0 otherwise. Right? And so that means if I want to count the total number of tests, well, it's all of the first round tests plus all of the second round tests. So if your sample was tested as an individual sample in the second round, we count that. If not, we don't count it. All right. Good. Now, this random variable, well, this thing that usually we would say it's an indicator random variable, but we have to be a little bit careful here because there are some people here that, well, they'll always be tested. In fact, that better be the case if this works correctly, right? Because some people are infected, and we need to identify those infected people, which means that they need to be tested in the second round. And they will be tested in the second round because in the first round, an infected person is part of an infected group because they make it infected just by themselves, which means that group will be tested individually in the second round. So we sort of need to distinguish between who's infected and who's not. So let's define I is equal to the set of indices such that group I, no, not group I, PI is infected, and N is just going to be all the other people, the people who are not infected. So we have in the problem statement, it says we have K infected people. So I is just going to capture those indices, the people who are infected, and N is going to capture the indices of the people who are not infected. There's K of these ones, and so therefore there's N minus K of these ones. All right, but now we can split this thing up. So this is N over S. And instead of summing over 1 through N, let's split it into the two groups. There's the infected group, and there's the not infected group. And the thing about the infected group is they will always be tested. People in that group will always be tested the second time, in the second round. Okay? So this xi here, it's not really a random variable for people in this group. It's just equal to 1 always. But this thing here, this is a random variable. So if I'm not infected, and I happen to be in a group where nobody else is infected, then that's great. My sample won't have to be tested the second time. But if I'm not infected and I end up in a group where someone else is infected, then my sample will be tested the second time. So, and now of course we want to know the expected value of x. And you know, this says, well, we can take expected values here. We're going to get an n over s. This is going to be k, right? This is just the sum of k1s. And then this thing here is the random thing. This is an indicator random variable that is 1 or 0 with certain probabilities. So each of these. So we need to figure out the expected value of this xi for these people who are in the not infected group. So we want to know, for these people, expected value of xi, and this is for i's in this set of non-infected people. And we know with indicator random variables, this is just the probability that xi is equal to 1. They're really simple indicator random variables. All you need to know for their expected value is the probability that they're equal to 1. All right, good. So when is xi equal to 1? Well, xi is equal to 1 if in my group, I'm the uninfected person, pi. If in my group there's somebody else who's infected, who ends up in my group, then xi is equal to 1. And that actually gets a bit annoying because if there's one other person in my group that is infected, then I will have to get a second test. If there's 2 other people in my group who are infected, then I'll have to get a second test. If there's 3 other people in my group who are infected, then I'll have to get a second test. And we don't want to have to compute all of those probabilities and add them together. That takes too long. So we'll do what we always do in these kinds of things, which is we'll use the complement rule. So let's define AI is the event no one in PI's group is infected. Because then, not AI, the complement is someone in PI's group is infected. And if someone in PI's group is infected, that's the same thing as saying that PI needs to be tested a second time. Their sample needs to be tested individually, which is the same thing as saying that xi equals 1. So in particular, the probability that xi equals 1 is equal to 1 minus the probability of A. All right. So all we need to do is figure out this probability of AI. And this is an interesting one. Because you can actually solve this problem lots of different ways and get lots of different looking formulas. So I'll do it so that we get the same formula that's in the book, though maybe with a slightly different proof. So the book contains 2 different proofs, one of which is naturally gives you this formula, and the other of which is maybe more familiar to you, so it doesn't skip any steps, but gives you a different looking formula that then you have to beat up in order to get the formula that matches the first solution. So I'll try and combine the 2 so we get the good looking formula with the proof that we're sort of familiar with. Okay. So what's the probability of AI? Let's write that down, probability of AI. Well, remember this is a uniform sample space. And so that means the probability of an event is just the size of the event, so the number of outcomes in that event, divided by the size of the sample space. And this, the sample space, is just all the permutations of those people. So that has size n factorial. This is the thing that we need to compute up here. So, I have this one special person. I don't know, let's call him X. X is not infected, and I need to know in how many permutations of all those n people, including X, does he end up in a group where nobody is infected. So we'll use the product rule to count that. So here's the procedure. Choose, so we're trying to make a permutation of all the people. Okay, so we're trying to find all the permutation of all the people, and we want all the ones where X ends up in a clean group. So let's focus on X and choose the location for X. So we have n possible locations. So this is, we're going to line up all the people in some particular order. And, you know, here's a way to define how to do that. We choose a location for X. Put X there, maybe. How many choices did we have? Well, we had n choices. So that's n choices. Now, once I pick the location for X in this permutation, remember how the groups are made. They're just, you take that permutation and you break it into, starting with the first S and then the next S and the next S and so on. Now once I pick where X goes, well, that means I know which positions correspond to the things in X's group. So this is X's group. And it's of size S, right? All right. So now I want to choose the locations for members of I. Okay. So now there's a bunch of infected people. And I need to choose locations for them in this permutation. Okay. So that means I need to pick k places in the permutation and take the k infected people and put them in those places. Now, I'm trying to compute the size of AI here, and that's the event that none of those infected people ends up in X's group. Okay. So that means when I choose the locations for those k infected people, none of those locations should be in here. So that means I'm choosing them from a set of size n minus s. So I have n minus s options to choose from, and I need to pick k of them. Okay. So n minus s locations, there and there. I need to choose k of them for the infected people. And then I need to decide, those infected people, those are k different people. I need to specify exactly what order they show up in those places. Okay? So it's really, I need lots of ways to think about it, but this is a function from a set of size k, that's the k people, onto a set of size n minus s, and it's supposed to be injective because I can't put two things in the same place. We get a formula like that. But I mean, just think of picking the locations first, and then assigning. Once you've picked your k locations, assign an order on the people and put them in those locations in the order that they show up. All right. And all right, so that's the location. So what have we done so far? So we've seen a bunch of infected people. We've placed them now. And now there's a bunch of uninfected people that we still need to place. Well, what's left? We placed this one person, X, that we're interested in. We've placed these K other people that are infected. That means there's N minus K minus 1 places left to place the remaining people. And we have to choose what order they show up in that thing. So now we finally choose locations of N minus K minus 1 other, and these are non-infected people. And there's N minus K minus 1 factorial ways of doing it. And then that's it. Everybody's placed, and we get all of the possible permutations that don't involve putting an infected person in the same group as X. So by the product rule, that's the size of our set AI. We get an N, we get an N minus S, choose K, K factorial, and then we get a N minus K minus 1 factorial. And that thing divided by n factorial, which is a horrible looking formula, which I don't like. And you can beat it up into several different forms that are all the same. But rather than try and do that, let's actually, let's just count the number of permutations. Even though we know it's n factorial, let's count it another way that makes it more comparable to this. So, because what I was doing here, I was counting some of the permutations, but not all of them. So I was counting the permutations that don't involve putting an infected person in the same group as X. But maybe this procedure can also be fairly easily, almost the same procedure counts the number of permutations. And in fact, it does, right? So this is for the permutations in A. But if I want to know any permutation, I can build it like this. Choose the location for X. That's the same. There's still n choices. Choose the locations for the infected people. What's different now, though, is those infected people, they don't have to avoid being in the same group as, if I'm interested in any permutation, that includes the ones where some infected people may be in the same group as X. So I don't have just n minus s places for them to choose from. I actually have n minus 1. So each of those people infected people can go into any location except the one already occupied by X. And then I have to specify the order that they go in there. So it's n minus 1 choose k times k factorial. And then, once I've done that, I have to place the non-infected people in the remaining, there's n minus k minus 1 of them, and they have to choose the order that they go into those remaining slots. So we choose locations of n minus k minus 1 other non-infected people. And there's still n minus k minus 1 factorial ways to do that. So I get an answer, right? That counts the total number of possible permutations. It's a weird way to build a permutation, but certainly a way to do it, and it can build any permutation, and there's only one for each permutation. There's only one way to build it. And so that tells me that n factorial has a long-winded version, which is n, that's the first thing, n minus 1, choose k, k factorial, n minus k minus 1 factorial. So why would I want to go through all that effort to get a convoluted expression for n factorial? Well, because I wanted it to look like what was on top here. And it looks a lot like it, right? We have an n on the top and the bottom. We have a k factorial on the top and the bottom. We have an n minus k minus 1 factorial on the top and the bottom. So we finish with n minus s, choose k, over n minus 1, n minus 1, choose k. So that's the probability of AI. And then the expected value of xi is 1 minus that probability. So expected value of xi is equal to 1 minus n minus s choose k over n minus 1 choose k. Good. So now we can finish up this calculation. So this was just true for x. I mean, this is by definition, this is the value of x, which means that the expected value of x is equal to the expected value of this thing. We have expected value of a sum. So we take the sum of the expected values. The expected value of n over s is not even a random variable, so it's just n over s. This thing here is also not a random variable, it's just going to be k. And this thing here is a sum with some random variables, so we can bring the expected value right inside. Like so. And then we finish with n over s a k. The number of terms here is, there's one term for each non-infected person. So there's n minus k non-infected people. And the expected value of xi for each of those people is 1 minus n minus s choose k over n minus 1 choose k. Okay? So that is, if we use this procedure, that's the expected number of tests that we have to perform. Okay? Good. So, not easy to understand exactly what's happening here. I mean, it's not super intuitive. And of course, it shouldn't be, or normally it wouldn't be, because there's a few parameters, right? There's the number of infected people, N, that's also a parameter, and then S, the size of the groups that we use. So, I mean, the best thing to do now, once you have this nice, cleanish looking formula, is, well, you're a person who needs to use this, so go and look for your value of N. How many patients do you have? How many people do you have? How many of them are infected? Then look at the values of S, plug in different values of S to see what kind of numbers you get. And that's what we'll just take a quick look at a couple of examples now. So from the textbook, so he likes the example, N is 1,000, K is 10. So you have 1,000 people, 10 of them are infected, so that is a infection rate of 1%. And if you use groups of size 5, then you require about 249 tests. This is just evaluating that formula numerically. And if you use groups of size 10, you get 196 tests. And if you up the group size again, you get 234 tests. So somehow between 5 and 20, it dips down to 196 with group size 10, and then goes back up again to 234. And of course, you can just plot this thing and see what it looks like. And indeed, from a group of size 5, what did we say? Well, already for like a group of size 3, you're up to 350. It drops down to about 250 at 5. And then the minimum looks like it happens in groups of size 10 here. So 10 is the best choice of S here. And it means you can get by with 196 tests. Still a lot better than the 1,000 tests that you would need if you weren't doing this this kind of pooling. Okay. All right. So that's called single pooling, which I'm not even sure why the term pooling comes from, other than, each group looks a little bit like a swimming pool that everybody has spit into in that group. I don't know. But that's called single pooling. It's been known for a long time that this is a efficient way to save effort on tests like this. But actually in 2020, sort of at the beginning of this pandemic, there's a couple of computer scientists who wrote a short note just observing that this isn't always the most efficient way, the most efficient use of resources. And these particular authors actually, they have a history of, so they worked in hashing before. So hash tables, load balancing, this kind of stuff, where there's this notion of the power of two choices or the power of more choices that somehow can often make things much, much better. And here's what they observed. So let's go back here and let's just remember this thing. So in particular, let's remember this probability of AI. So for a particular non-infected person X, the probability that no one in X's group is infected is this formula. Okay. So we've done the hard stuff now. We're going to see that actually what we're going to see next is a sort of easy trick to do better than this. So, new procedure called multiple pooling. Works as follows. So take C different random permutations of the n people. So let's call them, I don't know, pi 1 to pi c. Maybe take 2 different permutations of the people, or 3 different permutations, or 5 different permutations of people. Okay, so, you make, this defines the groups. Let's call them G, I, J. So I is in 1 to C, and J is in 1 to n over s. Okay, so I have my first permutation, pi 1, the people are in this order. And then there's pi 2, same people but in a different order. Then there's pi 3, same people again but in yet another order, and so on. Now I have this procedure for defining groups, which is, to get one of these groups, the first one of these groups, I take the first S people here. So that is the group 1, 1. But if I take the first S people here, well, that's another group, 2, 1. And this is the group 3, 1. And this is the group C1. So this here is GC1. And anywhere I go, right? So, there's going to be, this is all broken up into groups of size S, and there's a corresponding group in each of these things. All right, so how many groups is that? That is n over S times C. N over S in each row here, and then there's C rows. So now you say, for each person, we've been calling individual people X. So for each person X, no, not, sorry, not yet. For each group Gij, test group Gij. Okay, so we said that that is going to be C times n over S tests. And now for each person X, you say if every one of X's groups, that means all C of them, tests positive, then test X. Right? So remember, I have permutations pi 1, pi 2, pi 3, pi 4, pi 5, up to pi C. If I look at a particular person X, then X appears somewhere in this permutation. And that means that they appear in some group in this permutation. That's in permutation 1. But X appears also in permutation 2, somewhere, like there, for example, which means they also appear in some group, there. And then X appears here, and so on. Now, if any one of those groups comes back testing negative, so I did a test for this group and it came back negative, that means X is negative. So X is not infected, right? Because if X is infected, they will infect, the test for every one of the groups that includes X will come back positive. But, so if one of those tests comes back negative, that means X isn't infected. So we don't have to bother testing it. So that's all this says, is if every one of X's groups, so there's C of groups that X finds themselves in, one in each permutation, if all of them test positive, then we have to test X. But if even one of them tests negative, we don't have to bother testing X. All right, that sounds good, right? We've gone from somehow X having to fail one thing, to get unlucky once to be tested a second time. Now X has to be unlucky C different times before they need the final test. All right, so now let's say Y is the number of tests. We're interested in the expected value of Y, and we can start writing it down. Y is equal to, well, there's a big overhead cost, because now instead of doing just n over s tests, we have to do C times n over s tests. And maybe that'll save us enough of this second round testing to be worthwhile. So Y is going to be C times n over s plus, well, we can split that sum same as before, where we take I in the, or let's say X, in the infected set of people of Ix plus we take x in the non-infected set of people, sorry, not Ix, and let me just, let's call this xi, and let's call this xi. So just like before, we have the first round of testing. In the second round of testing, there's a difference between infected people and non-infected people. The infected people will always get tested in the second round of testing. Why? Because an infected person will infect every one of these will make every one of these groups test positive, and so so they will get tested again. They'll pass this test. Every one of the groups that they're in will test positive, so we'll test them. And then it's just a question of these non-infected people. How many of them get tested? So this number here, the number of tests of infected people is every infected person. So it's K. And what about this number? So what does it mean now to say that this person got tested in the second round? Well, that means that this person was tested because this group has a positive, at least one positive person in it, and this group has at least one positive person in it, and this group has at least one positive person in it, and so on. So actually, we can go back and reuse what we just did. Right? So xi is going to be equal to 1. That's the same thing as saying person i's first group let's say pi's as an infected person and pi's second group as an infected person, and so on all the way up to pi's cth group as an infected person, c times. Now, pi's first group as an infected person, that's what we just computed. That was this 1 minus probability of A, right? It's 1 minus the probability that no one's group is infected. So probability that xi is equal to 1 is a 1 minus this thing. That's just for the first one. And then we have to check, it also has to happen in the second group. And the two permutations for the, pi 1 and pi 2, those are different random permutations. So in particular, the event that it happens in the first group is independent of the event that it happens in the second group. In fact, all of those events, that it happens in group 1, that it happens in group 2, that it happens in group 3, and so on, that's an independent set of events, and so the probability that they all happen is just the product of their probabilities. So, and they have to happen c times, so it's this thing to the power c. So now we can finish this up, right? We were looking for the expected number of tests. There's these tests that always happen, these tests that always happen. Now we need the expected value of this xi, which is equal to expected value of xi is given over there. And there's n minus k of these things, same as before. Minus n minus s, choose k, over n minus 1, choose k, all to the power c. So that's the expected number of tests we perform if we do this multiple pooling with c different permutations and groups of size s. Now, is that better than before? Well, in particular, is it maybe the case that c equals 1 is always the optimal choice? All right. So if I take c equals 1, that just means there's one permutation. It's the original single pooling that test that I talked about at the beginning. Is there any reason to think that this would be better? Because you do a lot of extra testing up front here, right? I mean, if I decide to even take c equals 2, meaning doing 2 different permutations, that means in the first round I'm doing twice as much testing as if I was doing single pooling. It had better save me a lot in the second round. Is there a reason to think that it will save me a lot? Well, it could be, because this is n over s multiplying by c. On the other hand, this is a probability, and it's smaller than 1, and I'm raising it to the power c. So in one case, I'm multiplying by c, but here c is in the exponent. And so if this is small, it doesn't take a big c. If this is much smaller than 1, then it doesn't take a big c to drive this thing close to 0 very quickly. And that's multiplied by n minus k, and that could be worthwhile. And if you're good at working with these kinds of things, you can gain some intuition about what the optimal thing might be. Like, for instance, if you can make this into a half, then you're getting 1 over 2 to the c here times this thing, and you're only getting multiplying this thing by c. That sounds good, but then it's not clear if you make it a half what value of s you need. So the best thing is probably just to plug in some numbers, which we'll take a quick look at now. All right, so the best we could do with single pooling in this scenario was, this was 1,000 people and 10 of them were infected. We could find them all with about 196 tests. And if we do multiple pooling, we can get by with, if we take blocks of size 30, okay, this is for c equals 2. So for c equals 2, we can use blocks of size 30 and get down to size 25, we can get down to 137 tests. So that already beats 196. For c equals 3, we can get by with well, he doesn't tell us the number of tests here, but I guess it's not the best one. And for c equals 4, so if we're willing to take 4 permutations, we can get by with 114.5 tests on average. So certainly beats 196, and does, I mean, that means that we're
basically saving nearly a factor of 10 versus the naive approach of testing every single person individually. So that's your lesson for today, how even this basic things that we've looked at in this course have some real world applications. And actually, it's worth taking a look at these notes because there's a couple of nice links. There's an article on group testing, but you can actually find, he has a pointer to a list of countries that are actually doing this. So they're implementing pool testing this way. So I know that Germany was in that list, and a bunch of others as well. So it's worth taking a look at. And that's all for today. I will see you on Wednesday.